Hi, I'm Han Wu, also known as Wuhan Studio on GitHub. I'm a third-year PhD student at the University of Exeter in the UK. In the following 15 minutes, I will introduce RTOS, a real-time operating system. Maybe it's more intuitive to show you a short demo first. This is RTOS running in a simulator. If I zoom in a little bit, this is the command line interface so that we can interact with the operating system. If you are familiar with Linux, here we have Ubuntu. In Linux, we can use the command free to check the memory usage. You can also use the same command in RTOS. Say, for example, we can see the total memory and the used memory. There is also a file system. In Linux, you can use the pwd to see the current working directory. Currently, we are in the home directory. We can also use the same command in RTOS. So if I use pwd here, this represents the root directory. You can use cap to see all the commands available. Well, maybe let's try something more interesting. As I mentioned before, this is Ubuntu. So we have a cow saying hello Ubuntu. We can also use the same command in RTOS. Let's say hello RTOS. Sorry. Now we have a cow saying hello RTOS. So the same program runs on both Linux and RTOS. As you may have already noticed, we even have Python here. So let's try Python in RTOS. Actually, this is MicroPython for microcontrollers. If you are familiar with Python, we can import a library using import. And we can print out some messages using the function print. And of course, we can return to the terminal using the function exit. So this is how we use RTOS. Let's move back, a short demo. Let's move back to the slides. Actually, there are 3 different versions of RTOS: the nano version, the standard version, and the smart version. In the previous demo, I used the standard version of RTOS. Well, the nano version, as its name suggests, is pretty small. It takes roughly 3 kilobytes of flash and 2 kilobytes of memory to run on microcontrollers. While the standard version includes more features such as a device file system, socket abstraction layer, and etc. Both nano version and standard version targets at middle to low-end microcontrollers, such as this one, if you look at the screen. While the smart version targets at high-end system on chips that has memory management unit, or MMU, such as Raspberry Pi 4. You can also check the documentation of different versions on the official website. This is a documentation center. We have documentations for standard version, nano version, and smart version. You can also check the source code on GitHub. The master branch maintains the code for the standard version. There is a separate branch for smart version. In the future, the smart branch will be merged into the master branch. So now you know that there are 3 different versions of RTOS. In the next slide, I will introduce each version one by one. The first one, the nano version, even though it is pretty small, it supports all the most popular inter-thread communication tools, such as semaphore, event, mutex, mailbox, and message queue. It also supports different CPU architectures, such as ARM and RISC-V. As you can see here, running 2 threads takes roughly 4 kilobytes of flash and less than 2 kilobytes of memory. It is extremely small and reliable. The next one is a standard version. As I mentioned before, the standard version includes more features such as key-value database, USB stack, device file system, Wi-Fi manager, and etc. It also provides socket abstraction layer and the POSIX layer. So the Linux command applications runs on RTOS as well, so that you can write applications that can run across operating systems. When I started learning RTOS roughly 5 years ago, I was amazed by the software package center. In Linux, it is pretty natural to use a software package manager to install softwares, but it's pretty interesting to use a package manager for microcontrollers. So for example, if you go to the software package center, we have a software package manager for RTOS. There are over 600 packages available here. We have different kinds of softwares: IoT, peripherals, system, programming language. I showed you how to use MicroPython, tools, miscellaneous, multimedia, security, AI, and Arduino. RTOS also supports some existing Arduino packages, mostly provided by Adafruit. And the last one, signal processing and control. Actually, this is new to me. Let's take a look. Of PID and common filter. So we have different kinds of software packages in the software package center. Let's move on to the next one, the smart version. As I mentioned before, the smart version targets at high-end system on chips that have memory management unit, or MMU, such as Raspberry Pi. It uses a microkernel architecture. For Linux kernel, it includes the device driver and file system, and etc., making it relatively large, several megabytes. While the RTOS Smart is a microkernel, it only contains basic functionalities, making it very small. It requires only 500 kilobytes. It also supports user space processes as well. As I mentioned before, you can try RTOS on Raspberry Pi. Now that you know there are 3 different versions of RTOS: nano version, standard version, and smart version, you may ask, well, how can I use RTOS on my hardware? Well, currently RTOS supports all the most popular instruction set architectures: RISC-V, ARM, MIPS, and etc. You can find the full list on the official website. So if you go to the supported board, you can see a full list here, and the list is still growing fast. Of course, you can also check the source code directly. If you navigate into the BSP folder, you can see all the development boards supported by RTOS. Well, you may say, here we have so many folders. This looks scary. I don't know where to start with. Well, in this way, I would suggest using RTOS Studio, the IDE, or integrated development environment. It has a built-in simulator, so you can use RTOS without a real hardware, and it's community-free. In the previous demo, I already showed you how to run RTOS in a simulator. This is the built-in simulator. We can also add some software packages directly from the IDE. So this is the built-in software package center. Say, for example, if I would like to use Python, or actually MicroPython in my project, I can search for Python and add it to my project. I've already added it to my project. So as you can see here, I added 4 packages here. If you press Ctrl+S to save the configurations, the RTOS Studio will clone all the source code of different software packages into your working directory or working space. Maybe I can show you how to create a project from scratch. So if you right-click here and choose New Project, you can create a nano project or a standard project. You can create the project based on a microcontroller or on a specific board. Say, for example, I can choose different microcontrollers from here, and I can choose different development board. So this is how we create a project. You can also add more development boards through SDK manager. This is the SDK manager. So as you can see here, the RTOS Studio supports quite a lot of development tools. You can also download the toolchain, the TCC toolchain from the SDK manager directly. So this is a brief introduction to RTOS Studio. As I introduced before, there are over 600 software packages available in the Software Package Center. These are the most popular components provided by RTOS: the command line interface, microblog, microlog, microtext, system view, Cortex-M backtrace, memory performance, just to name a few, RDB, KDB, and ADBD. RTOS also supports Robot Operating System, or ROS. If you are familiar with robotic applications, ROS is widely adopted in the development of robotic applications. Just in case, if you are not familiar with ROS, here's a short demo. I will introduce ROS using one of my previous projects. My research focuses on real-time adversarial attacks against learning models. So for example, this project uses ROS, or Robot Operating System. This is a simulated environment, Gazebo, the Gazebo simulator provided by ROS. Here we have a simulated robot. On the left side, you can see the image captured by the virtual camera. This is how we attack an object detection model. As you can see here, from the perspective of human eyes, we know that there isn't any project here, right? But after generating a human unperceivable perturbations, the object detection model detects traffic signs everywhere. This is how we attack an object detection system in real time. Let's move back to the slide. So you can also use ROS on RTOS. For middle to low-end microcontrollers, you can use ROS Serial and MicroROS. ROS Serial is designed for ROS version 1, while MicroROS is designed for ROS version 2. While for some high-end systems on chips that can run RTOS Smart, you can use the full version of ROS. Say, for example, you can use RTOS Smart on Raspberry Pi. It supports the full version of ROS. Maybe I can show you using another project. In this project, we attack an object detection system using a Raspberry Pi. This is a man-in-the-middle hardware attack against object detection. Say, for example, here we have a USB camera and a detection system. We have a Raspberry Pi in the middle. The Raspberry Pi reads the image from the USB camera, inject the perturbation, or apply the attack, and simulates a virtual camera to the operating system. The operating system has no idea the camera is under attack. After injecting the perturbation, as you can see here, the object detection model detects a lot of different objects everywhere. This is how we use a Raspberry Pi to attack an object detection system in real time. So we should really think about deep learning secure for robots. So this is a brief introduction to ROS and RTOS. If you find RTOS interesting and helpful, here is university program that provides some hands-on labs, online courses, and training. These are some pictures. We also have some books that can help you to learn RTOS. Of course, feel free to create a pull request on the GitHub repo so that you can collaborate with the community. RTOS was created in 2006, so it has been roughly 17 years. More features will be included in the future. So this is the end of my presentation. Thank you.